So we made the fixture plates, and originally I was going to have they fit in the T-slot, and I was going to have crossbar going across. And then I thought about the amount of time it would take to apply the crossbar and then index it one and apply it again, because there's a total of 80 cuts. So if it takes an extra minute to do it that way, that's an extra 80 minutes it's going to take me to cut all these slots. So I'm looking for a quicker way to clamp. Right now I'm going to use the parallel sides of these at least to position the stock. And I'll find I'm looking for a quick way to clamp and unclamp it so I can quickly cut the slot, move on to the next one. Next problem, low temperature plastic. This is polypropylene, melts around 500 degrees Fahrenheit. And as a result, it's going to tend to stick and melt to your saw blade and your milling cutter. So what I looked for was special blades. So for my table saw to cut this to a 17.2 square, got a plexiglass and plastics blade. And the shape of it's designed specifically to provide more clearance behind the cutter. It's probably a softer carbide because they're not expecting hard, because they say it doesn't work on non-ferrous at all. And it's a high tooth count blade. Typically, if you're going to cut aluminum on the table saw, you use a high tooth count blade, but I'm guessing that the grade of carbide on this is designed for sharpness and not, and hardness rather than toughness. The different grades vary that way. So I'm suspecting that this is to hold the edge longer, because sharp is what you need to cut plastic. And then the cutters, I got a 2 and 3 flute. Let me grab these real quick and pull these out of the package. The two cutters are of a specialty variety as well. I was originally going to use 2 flute milling cutters, but looking at the geometry, probably not ideal for plastics. These are special plastic geometry cutters with a huge amount of relief behind the cutting edge, very, very sharp cutting edges. You notice how thin that web is. Everything's designed to give the chips the least possibility of sticking and adhering to the cutter, because once that happens, you're not getting a good cut anymore. This is a 2 flute cutter, and the other one is a single flute cutter with a huge amount of chip ejection. So having never cut plastic, I did a little bit of research, and these are the cutters recommended. So hopefully we'll be able to get a good finish on the plastic. All right, so we're gonna hop onto the table saw here, and I've got to remove this big aluminum plate I have on my table saw. I use that to weld on. Even though cast iron's good, I really didn't want to damage the cast iron surface, so I use this 1-inch aluminum plate I found to weld on top of. So I got to move that, and I'm going to use the table saw to cut this with this blade. And once I get this to size, then we'll head over to the milling machine and cut slots. So even with the plastic cutting blade, it's welded itself right behind the cut. Look at that. It just got hot, even though I used a specialty blade. Look at that terrible finish there. And I have no way of slowing the table saw speed down, which is what it probably needs. Maybe there's an easy way to clean off that debris. Even with the right blade on here, still end up with all this crap on the side. It's a real pain in the butt to deal with. However, the solution is to use this guy along each side. That gets rid of a fair amount. And then you take, this is a planer blade. I don't know if you can focus on that. This is a planer blade, and I take and I run it along the side and just scrape, and you get all the extra debris off. So I'm going to finish that up, and we'll have the 2 pieces cut to size. I don't know if you can see the focus, but I don't know if the focus ain't good. But when you're done, you can get an edge that looks like this. It's not great. Well, not perfect, but it's acceptable. So we're going to go from there. I'm a little afraid what's going to happen when I mill this stuff. Hopefully I'll slow the cutter down and we won't have this problem. I don't want to have to use coolant. Alrighty, so next up I think we're going to try some tests here to see if I can actually get any kind of a clean cut. So we're going to try different feeds and speeds. We're also going to try 3 different style cutters here. As I showed before, these 2 are specifically for plastic. Single flute, double flute, really high helix with large relief. And this is a ball end mill with a 40-degree helix, so it's designed to eject chips better. I really would like to do round bottom holes. It would make it easier for cleaning, but I don't know that this is going to be able to remove chips well enough. These are kind of small flutes, but we're going to give it a shot anyways. Maybe we'll start with that and see if we go from, you know, bad to better or worse to better, something like that. Anyways, so let me set this up and I'll bring you right back. All right, first thing we're going to try, what I think is going to work to the least extent, is the solid carbide, very sharp, uncoated, 1/4 inch round nose end mill. And we're going to start at low RPM, and if that doesn't melt things but can't eject chips, we'll try a higher RPM. Another suggestion I've read is that you need to use lots of air when you're doing this, so I could try that, but you won't want to listen to that. So if I end up having to do that, I will do a bunch of test cuts, and I'll bring you back and let you know which one worked out best. So right now I'm trying to do a 9/16 depth of cut as a test. I'm trying to do it in one go. It really would be nice. It looks like kind of a big cut for such a small diameter end mill, especially when the web is smaller. On the other cutters, it'll be especially a big deal. So I don't know if it's even going to work, but we're going to give it a shot. So we're going to start pretty slow. Let's try 700 RPM. We'll see if we can eject some chips. Oh, that's actually cutting kind of like butter. And I don't see any melting so far. Oh. Well, so far so good. All right, so here is an unretouched single pass look at the cut from this end mill, and it's actually really good. Boy, this is better than I thought, because I can tell you on the table saw, I consider buying that specialty blade a total bust. It melted the plastic. I couldn't slow the RPMs down, so the table saw was at what was it, 3600 RPM by default, I believe, and there's nothing I could do about that. Oh, it looks like this pulled up a little bit. Clamping this in this sort of method that I'm doing now, not ideal. Just between two vice jaws, just catching a little lip over here. It's a little over 1/4 inch is all I'm grabbing, so plastic is very flexible. Probably not the greatest idea. I'm going to try another pass at slightly higher RPM, see if I can remove chips even a little better, and see how that works. Okay, same cutter, pass at 1200 RPM, and I'm going to manually feed. So they recommend a high feed rate with plastic in order to eject the chips efficiently, so I'm going pretty fast here, and that looked pretty smooth. Let me clean up some chips and take a look. There's the second pass. When I brought the first end mill back through the same slot, it kicked up all of these nasty little bits right here. Left the inside fine, but yeah, it tore up some nasty stuff here. I'm going to try the same here, see if it does the same. When we're going the first way, we are climb milling, and when we're coming back, we are conventional milling. So maybe that's the difference. So it looks like the material pushes out of the way on the way through because it did the same thing coming back. All right, let's try a different end mill, one of the specialty ones. All right, next up we have the 2-flute plastic cutting end mill with a spiral upcut so it ejects chips up. And they want you to not leave too much of this material exposed, so we're going to try that. Here's 700 RPM. All right, so there's the finish on first pass through. It broke out the other side, and it made a little snapping sound as it broke the plastic, and I actually thought I broke the cutter, which really kind of freaked me out, but it didn't. Let me bring the cutter back through and see if it turns up a bunch of fuzz like that. Not that I ever need to do that, but I'm just curious. So like the other cutters, it does remove material on the way back as well. But it did not turn up a burr, so cleaner cut. All right, now let's try the exact same thing, except turn it up to 1200. See if it breaks out the other side. I truly was having serious anxiety about coming and doing this, all the slots, because I thought it kind of broke out the other side too. Let me clean it up, bring you back. So, brought the other, this, you can see when the other color came back through, it didn't turn up fuzz like these other ones here. The higher speed just let me feed it faster. Still cleared chips fine, so that's all good. This is no coolant, and some people that are cutting plastic use compressed air. Even better is to use cold compressed air, but then you need a really big compressor because they take a lot of CFM, cubic feet a minute, to be able to do that, those air coolers. I think they're called Venturi coolers. In any case, I'm going to switch over to the single flute. This one also broke out the other side, although I didn't see any damage to the material, but it does make a big snap. Kind of freaks me out when it does that. Probably not the best on anything either. So we're going to bring the cutter back through. We're going to switch to the single flute, which I think will break out even worse. We'll find out. All right, so next up we have the single flute cutter, and it ejects chips better than the other ones, supposedly, because it's a much bigger flute. But it's also going to be putting force only on one side of the cutter, so got me a little bit spooked here. So we're going to start at 700 RPM again. Oh wow. Yeah, this one, it does eject chips a lot better. It's like making little baby soda straws. That's kind of neat. Very clean cut. Ooh, but the breakout the other side was much louder. Let me clean this up, bring you back. All right, so very clean cut as well. And I'm going to bring the cutter back through, and like all the other ones, I expected to take off material, which it is. And next up, we're going to go for 1200 RPM. Very clean cut. Did turn up a little bit of a burr. So let's move over a little bit. Hop up to 1200. Yep, broke out the other side. And we're going to clean this up. I'll bring you right back. Okay, here's the 3 slots. Now, the first 2 were done by the ball end mill, and you can see the round bottom on them. And this crap on the edges here was only turned up after I brought the cutter back through, which I won't be doing. These guys here, you can see that they're very clean. The second one, the second 2 flute, not quite as clean as the 1 flute. They all turned up a little burr on the exit here. They didn't break out any material, even though they sounded like they were. Sounded really kind of horrific. So now I just got to decide if the customer really would prefer to have a round-bottomed slot for ease of cleaning, then I'll probably be using the round end mill. And it's got to make sure I do conventional milling, not climb mill. I mean climb milling, not conventional milling, because that produces a better finish. I'm going to switch back and do another test real quick, just so you can see. All right, for this final test, I want to compare the ball mill, since it turned up such a nasty burr on the return pass. What I'm going to do is I'm going to go all the way through with climb milling, and then I'm going to come back with conventional milling, but never go over the same groove twice at 1200 RPM, since that seems to be fine. Completely different chips from this end mill than the plastic-centric ones. Okay, that was climb milling. Let me clean this up and do conventional on the way back. All right, so here's an interesting result. Climb milling, conventional milling. Notice the burrs. So conventional milling with a ball end mill, a 2 flute, causes substantial burrs to be formed. So you want a climb mill. Isn't that interesting? Much better finish. Although in no case is the conventional end mill as good as the plastic specific cutters. They're very clean edges. All right, so I was just curious what the wall finish looked like, so I took my bandsaw and I just cut across a bunch of these. So here you go. Hopefully you can see this. Let's see if I can get the light on. Okay, so the two with the really rough walls. Now I was feeding this really fast. Oh, jeez. So I was feeding this really fast, but the finish on the two with the single flute and the double flute plastic specific end mills, you can see the really rough finish. You can see here, see how smooth that is? That is the ball end mill, the two flute ball end mill. Much, much better. So for food kind of thing, I think we're going to go with a conventional milling cutter rather than a plastic specific, because you don't want lots of nooks and crannies when you're trying to clean stuff. So even though it's just for dogs, I'm sure he said he's extremely careful with cleanliness. One more thing before I go, I just want to point out this end mill is solid carbide, as are the two plastic cutting ones, because that's pretty much all I buy. Solid carbide end mills just hold their edges better if it's not an interrupted cut than high-speed steel. And in the old days, they couldn't make them as sharp, but now with modern techniques, carbide end mills are every bit as sharp as the high-speed steel counterparts. At least I can't tell a difference. But one thing I didn't get, which I usually do, is a coating on the end mill, because they can make the edge last a lot longer, especially at high temperatures. This is an uncoated carbide end mill, and for plastics it's recommended, because when they put the coating on, like titanium nitride, that vacuum vapor deposition or plasma vapor deposition, however they're depositing it, puts a layer over the already sharpened cutter, and it makes it slightly duller. It rounds over that sharp edge. So important for plastic is sharp. So get uncoated cutters. At least that's what I have read. Right, so there's been a little bit of change of plan. I'm no longer going to use these slots with a crossbarred index. I'm just going to drill and tap because the indexing will be done by a plate on the top that I mount to the mill table. You'll see in just a few minutes. So I'm just drilling and tapping to hold the crossbar down in place, and I'm going to drill and tap both sides here, and that'll give me some flexibility. We're going to do both pieces, and then I'll bring you right back. All right, so here's my setup. I've got this plate in back, and I've surface ground it to be flat on this side, which I put arrows to show which side. Actually, I made it flat on both sides, but ran my indicator across it to get it square with the motion of the waves. I've got my two side blocks over here, which I shortened because I need as much cutting space here, I didn't think about that, as I possibly can. I'm still going to have to move them when it comes time to doing the final slots. The crossbar here is I have thumb wheels. I wish I had bigger ones, but I don't. They're spring loaded so that they pop out of the way. So what you do, let me just get this guy out, is I will slide the board in flush up with the back, tighten it down like so, then do my cut, pop it out, flip it 90 degrees, do my cut again, pop it out, flip it 90 degrees, do my cut again, 4 times each board, and then move on to the next slot. And that way I will be doing, I only have to go through half the board direction wise. Unfortunately, this bar is in the way for the first part, but I'll be able to move this this block to the center here and continue off from where I was. So this should be fine. Now that I've shortened them. If they were, when they were longer, you couldn't move it anywhere in here, and it just wasn't going to work. So anyways, we should be good to go. And we're going to get started here soon. We're going to start with the 1/2 inch relief all the way around the outside edges. And then once we're done, we'll start doing slots after that. So today I learned a valuable lesson about edge finders. So I've been using this electronic edge finder, which always has worked really well. But I thought that the conductive part was mounted on plastic, and I thought it was centered really well. I discovered I couldn't figure out why I was having repeatability issues. And I was thinking mentally about blaming my DRO, but in fact, The problem is the edge finder. So with this kind of rotating edge finder, it self-centers. And when you apply force to one side, it'll push it off center and it'll be readily obvious. With this kind of edge finder, every once in a while I bump the tip. I screw up and I go in too hard. I normally am very careful, but every once in a while I screw up. And I've actually bent the tip. And it's about, at the tip here, it's about 15 to 20 thousandths out. Which means if the spindle rotates while I'm making a measurement, even a slight amount, I could be off several thousandths. So repeatability is going to totally suck. Plus, if I go side to side, the center is going to be off, potentially by whatever the shift is to one side. So anyways, there's a definite downside to these electronic edge finders that you don't have with the spinning kind because they're spring loaded and they auto center. So lesson learned. All right, so these are really long cuts. We're going to bring the RPM up to about 1200 since that seemed to work. They didn't try it on the half-inch cutter. We're going to try a full half-inch material removal. I'm not going to full depth just in case the bottom finish is screwed up. As a matter of fact, I won't go to full width either. So I'm actually helping to support the material just from vibrating because one of the problems with this material is it varies by 40 or 50 thousandths in thickness depending on where you are in the cutting board. So it's hard to make a clamping solution that has any kind of precision. And cutting out the end is always a little disconcerting. So here's what's happened when you take a small bite and just remove 10 thousandths on another pass. Totally screws it up. I mismeasured, so we're all right in our half inch. But taking light cuts in the plastic leads for a pretty nasty finish. Fortunately, I'm going to come back and do the second half of this groove. I want to just see if I did a light cut all the way across, what would happen. Those burrs can be cleaned up. So here's the finish. I know it's hard to see because it's white on white, but pretty decent finish. I find that small bites are no good, big bites are better. Also, the plastic tends to push out of the way while it's being cut a bit, so the bigger the bite you take, the less likely that is to happen. It still happens some, so if you go back across the same cut, you're going to remove a little material quite often, especially if it's a groove. So interesting observation. Now I just need to do this 7 more times and I'll be right back. As an example of strangeness, so I purposely left the cut, so that's a half-inch cutter, and I probably should have gotten a 5/8 cutter, but I didn't. So I'm using what I've got here. But here's interesting. I only went in 0.499, so I left a thousandth overlap on the outside edge, and it still turned up this portion that is about 5 thousandths thick. So the plastic really deforms out of the way of the cutter. It makes it a bit challenging, so it might be better to do this in 2 1/4-inch passes each time, which will just take longer, but I think it'll get better results, and I may not get this weird scalloping on the bottom that I didn't get the first time I did this, but this time I did, so we're going to give it a shot. All right, we're set up here to do some slots, and I've learned a couple of things. One, I'm taking a lot of time having the end mill bringing the table all the way back to the opposite side, but I need to do that because if I don't climb mill, if I conventional mill, it turns up a burr, so that's a big problem and a total pain in the butt. So that slows down each pass, and since there's 80 passes, 88 if you include the outside, it's a lot of passes to slow down an extra 30-40 seconds, talking like an hour and change extra, just waiting for the table to move. Also, the material deforms and closes up behind the cutter about 4 thousandths out of a quarter, which is kind of interesting, 4 or 5 thousandths out of a quarter. That seems to be consistent. Also, the material is not homogeneous, and that means consistent throughout. So when you're cutting, sometimes it cuts perfectly cleanly, Same cutter, next pass, maybe not. The next one after that, maybe perfect again. The material also varies by over 60 thousandths in thickness, which makes clamping really interesting and challenging and annoying. Trying to get any kind of accuracy is really a bit of an issue. I read that online, and boy, they weren't kidding. Fortunately, this doesn't need to be incredibly accurate, but I'm still, like always, trying. Sometimes we get burrs, and cleanup is going to be a big pain. You can always scrape it with the scraper like I showed earlier, and deburring tools seem to work pretty well as long as they're really sharp, but this material is definitely a challenge. So I'm going to do a slotting pass, and I'm using instead of using compressed air, I'm using a vacuum, so you're going to have to listen to that to clear chips, and that makes it so I don't risk breaking the bit. My feed rate is pretty high. (1200 RPM). At the end of each cut, I retract the board away from the stop, which I indicated in, and I bring it back so that the cutter is always climb milling. That gives the smallest amount of burr. Here's my first cross-cutting hole. Alright, so I'm continuing along multiple passes, and I'm discovering another nasty feature about this material. I would have thought the thermal set material wouldn't, since it was, hot liquid to begin with, I wouldn't think that they would instantly cool it, but maybe they do. Maybe these are rapidly cooled because there's internal stresses in the plastic, and as I cut it, it's warping, which means the cuts aren't all staying the same. So if you look down here, it's warped up about a 1/16. So what I think you need to do is you need to make a fixture that's going to hold flat on either side of the cutter the whole time. I did not. Fortunately, this is not a critical part, but boy, if it was, what a miserable challenge this thing would be. Anyways, I'm going to continue along here. Just thought you'd want to see the progress. I'm getting like maybe 12 to 15 of these passes an hour lines. So there's 40 here. So we're looking 4 to 5 hours minimum just for this portion of the project. So if you bid this stuff, keep that in concern. I have to still go back and hand deburr everything because at the exit and entrance of every cut, there's a burr and it sticks, and you're gonna have to go in there with a sharp tool and remove it. So factor that in as well. That's probably another 4 or 5 hours for 2 of these. So I way underbid this. Interesting challenge, learning a lot. So there's no, it's not a really bad thing. But if I was in this to make money and it was my job, I'd be in deep trouble. To do the second half, just flip the clamps around to the back side, and I'll be able to cut all the rest. However, I have a problem with significant warpage. Look at that. I wonder if heating it in the oven between 2 aluminum plates, at 200 or 300 Fahrenheit would be enough to soften it up and straighten it up. I don't know, because this is really bad. And the cuts out here are going to be, actually I'll probably only need to go to here. So all of my cuts will be covered, so that's good. Because remember, I'm flipping it 94 times, so I do one on this side, then when I flip it around there'll be one on this side. So I only need to go to here, so it'll always be supported by the table, which is good. However, this warpage is going to be a significant problem if I want my depth to be controlled at all. So we're going to see what we can do about that. Final product with several mistakes because I didn't compensate for the cupping in a couple spots, and it totally hosed me. I had to actually put a bunch of weights on the end of it and lean on it on the final cuts. Have to come up with a different clamping solution if I'm going to make another one. And there you go. You can see how badly the plastic cupped after being cut. Never seen anything like it. I didn't think this was like wood, or I think there was a lot of stress built into plastic, but apparently there is. Anyways, thanks for watching. Hope you find it useful. Hope to see you next time.